Hey guys, I'm going to go ahead and start topic 10 today. We're going to start in topic 10.1. Title of that topic is Arcs and Sectors. By the end of the class today, you're going to be able to find the arc length and sector area of a circle and use them to solve problems. And the whole point of this lesson is how are arc length and sector area related to the circumference and area of a circle. We know circumference by now. That's the line that creates the circle. The length of the circumference would be the same as if I could take the circumference, lay it in a straight line, and measure it. And we know what area is. We haven't explicitly learned the area of a circle, but we're going to do that in this topic. I have a few vocab words for you and just some ideas before we actually jump into anything, just so you know where we're at. Your central angle of a circle is an angle formed by two radii where the vertex at the center of the circle. So if we look down here, this right here is P is our center point, so we would call this circle P. And then these two line segments, or radii, form a vertex, and that is called your central angle. So we have two. We have a smaller central angle at APB, or this red piece here. And we also have ACB, which is this major black piece of the circumference. If I take the black piece and I add the red piece, I'll get the entire length of the circumference. And as we know, the total measure of a circle is 360 degrees. So ACB plus AB must be 360. That's one way to check to make sure we're doing everything right. The intercepted arc is exactly what I'm talking about. The red piece here is intercepted by these two radii here on the minor part, and on the major part, ACB is intercepted by the two radii. So let's just actually read it out. Intercepted arc is the part of a circle that lies between two segments, rays, or lines that intersect the circle. A central angle and its intercepted minor arc have equal measure. The total measure of a circle is 360. The total arc measure of a circle is also 360. So that means this measure here, angle APB, is equal to AB's length. If I say minor arc, and I kind of already did say minor and major, the minor arc is the part that's less than 180, and the major arc is the part that is greater than 180. Of course, if our line is 180 degrees, then we just have a semicircle. Semicircle is a circle cut directly in half. So if you have a diameter that is straight across, you have a straight angle, you've created a semicircle. That is this word right here. Here it says AB, and it's color coded for you, is your minor arc, and APB is a central angle, and AB is its corresponding intercepted arc. So here's your central angle, here's your intercepted minor arc. The major arc is the part that is larger than the semicircle. ACB in blue here is your major arc. Alright, so let's look at this central angle here. This is APB. This is the angle created by the two radii. That's why it is our central angle, because the radii originate at the center and they touch a point on the circumference. So APB is 95 degrees. Well, if we go back here, we know that a minor arc of a circle is an arc that is smaller than a semicircle. That is smaller than 180 degrees, as it shows. It also tells us that whatever this angle is, this arc length is also the same thing. So the degree measure of arc AB, and that's what this line means. See how it has curvature instead of a straight line? So it's not line segment AB, it's arc AB, is equal to the measure of its corresponding central angle APB. So if I were to ask you for the arc length of ACB, well, let's not do that first. Let's find what are the arc length or the measure of arc AB. Well, whatever this arc length is always equal to this central angle measure. So we can go ahead and say that AB is equal to the measure of angle APB, which is 95. Now, if I know the whole thing is 360, this is going to be similar to what we were doing with triangles. The whole circle from A to B to C and back to A is 360 degrees. And I've already taken out 95 to find what's left. I'm going to do 360 minus 95, and that'll give me A to C to B, because this is the major arc with the portion we're looking for. We're going to subtract the minor arc out, and that gives me 360 for the whole thing minus the minor arc. And if I pull the minor arc out here, think of this as a wedge I can slide out, then the blue piece will be 265 units. So the measure of an arc is equal to the measure of its corresponding central angle. So let's say we go back here and we were to bisect this. Then this angle would be cut in half. So would this arc. So we can say that AP, and then let's call this D. This wedge here would be half of 95, and the wedge on the right would be half of 95. That's kind of what we're seeing here. JL is equal to JPL, but they're both bisected. So JPK is congruent to KPL. Or JM, that is our outside arc. It's still not a major arc though, is it? So JM is this guy in red. It's not quite 180 degrees. 180 degrees would cut into JPK. So it's still another minor arc, but JM is congruent or equal to measure of angle JPM. And we have the same thing like I say here. JPK and KPL are the same. Therefore, their arc lengths are the same. JK and KL are the same. So really the number one thing you should be taking away from here is your central angle measure is always equal to its intercepted arc. So my intercepted arc is JK, and I have JPK. Now notice what we're doing there. We're just taking out the center of the circle. JPK becomes arc JK, and angle KPL becomes arc KL. So dropping the center point out, you get the same measure that you get for the angle in your arc length. Right. Remember that the circumference measures the distance around all of the circle, and the arc length is the distance around part of the circle. So the whole circle, the whole measure all the way around, if you go all 360 degrees, is the circumference. If you're only taking a portion of the circumference, then that is called your arc length. And again, arc length is another way to use the distance formula. It's going to be the same formula when we're working in degrees, but it's going to be a modified version of that formula. Sorry. Now when we work in radians, it's going to be a totally different formula. It only has two things going for it, and it's going to look really easy, and once you get the hang of it, you're going to find it to be much easier, I promise. So let's actually start looking at how to find the measure of the arc length. The number one thing I want you to take away from this part of the presentation is S in every class going forward will always be your arc length. S from this point forward is going to be your arc length. When you go to any other math class, when they start asking for S and you're dealing with curves, they are asking you for the length of the arc. So the measure of an arc is a fraction of 360 degrees, right? So the whole thing, if I were to start here and go all the way around, that's the circumference. But now that I have an intercepted arc, so this radius and this radius intercept this arc, that is when I'm going to find arc length or arc measure. So the arc length is a fraction of the circumference. So it's going to be this portion over 360. So the part n over the whole, which is exactly how you probably learn fractions, is think of it as the part over the whole. So arc length is always equal to arc length divided by the circumference, so that your part over your whole is equal to your arc measure divided by 360. So let's look at it and break this down really quick. All right, this is the part of the entire circumference that you're looking at, right? N is the intercepted arc, the piece inside the two radii, and you're dividing the part that you're considering by the whole circumference, or the whole 360 degrees. And when I'm finding a percentage of something, right, I find the percentage and then I multiply it by the whole, and that gives me the value of that piece that I'm specifically looking at. So here I have a fraction. Let's say n was 180. Well, 180 divided by 360 is 1/2. So I'm really looking at half of the circumference, and that'll give me the arc length. That's all that this equation is doing for us. So let's look at arc length in degrees and in radians. Now, your in degrees and theta, this is a circle with a little line through it. You'll see when I draw it as like a circle with a little hair swoop brush to the side, but in degrees will always be equal to your radians. There are two ways to express the same measure. You have typically only used degrees in this class and probably your whole life. I've kind of hinted towards switching to radians soon. When you get to higher math, you're going to want to work in radians all the time. It just makes everything so much easier. You're probably looking at these two equations and saying, well, yeah, this looks so much easier. If I know what my radians are, and then I just multiply it by the radius, I'm done. And that's kind of in this 360 being gone, and this 2 pi, and all of this together does simplify to that. Later on, it'll make more sense. But go ahead and get both of these down because we're going to be working in them back and forth. One way to identify if you're going to be using this formula or this formula is where does your pi exist. If you don't have a pi inside of your central angle for your measure, you're going to be using degrees. If you see pi as part of the central angle measure, you're going to want to work in radians from there. So let's look at a couple of the questions. What is the length of arc AD? Express your answers in terms of pi. See, just like I mentioned here, this is in terms of pi, and this is in radians. Your theta represents radians. So when this asks me to represent it in terms of pi, I know I'm going to be working in degrees for this problem. So I'm not going to get this much simpler equation to help me out. I'm going to need the part of the circumference that I'm looking at, the n over 360, times the entire circumference. So I need A to D. So do I go A, B, C, D? Or do I just figure out from A to D? Well, there's a couple things we'll see here. Notice this 4 does not have a degree sign. So that's going to be denoting the length of my radius. So AP, PB, PC, and PD are all length 4. APB, my central angle APB is 73 degrees. BPC is 43 degrees. CPD is 104 degrees. So it says find the arc measure. Note that each arc measure is equal to the measure of the corresponding central angle. So if it's asking for AD, that's going to be this piece here. I'm going to do 360 minus this, minus this, minus this. And I'm going to be left with 140. So this angle here is 140 degrees. So now to find the arc length, because we want it in terms of pi, we're going to plug in my measurement of my central angle APD, which I now know is 140. So that's my part over my whole. I'm going to multiply that times the circumference. Well, to find the circumference, I have to use the radius length of 4. And I'm just doing substitutions here. My n is the actual central angle value here of APD, so that's 140 times 2 pi 4. Now, one nice thing when you see in terms of pi, and this is where I'm going to predict a lot of people are going to make a few mistakes, just kind of like I've been doing since topic 7, saying, guys, be aware of this before you move on. When it says in terms of pi, your answer must have pi in the answer. Don't multiply by 3.14. Don't multiply by the pi button on your calculator. Make sure you just move pi right on out to the outside. And I'm going to have 2 times 4, which is 8. And 8 times 140 over 360. And that's going to simplify to 28 over 9 pi. Again, in terms of pi means make sure you have pi in your answer. If you try and multiply by an irrational number, you're going to have to round to submit your answer. And when you round, you no longer have an exact answer. And we want to be as precise as possible in this class. And to be as precise as possible is to give an exact answer every time. Now we're going to look at a sector. So what is a sector? A sector is a region bounded by 2 radii and the intercepted arc. That word bounded is going to be really important as you progress through math. You're not going to really see it in Algebra 2 very often. You're going to start seeing it in pre-calculus and calculus. Bounded just means, it's the part inside of. Kind of think of your yard is bounded by your fencer. If you don't have a fence in your yard, BDCHS, the property is bounded by our black fence on 109th and Central, and then up against the other property, and then along the back we have a little variation of different types of fences. Those are the boundaries. Bounded boundaries kind of mean the same thing. So we know how to find the area of a triangle, right? I could draw a line straight across here and we can find that, but we have a problem here. It's more like a baseball diamond. We have this curvature here, so we don't really have a method yet to find the area in there. So how do we go about doing that? Oh, what is the area of a circle? It's pi r squared. You'll notice that here again, we're looking at a percentage of the entire circle times the area. Why does that work? Well, pi r squared will give me the entire circle. My r is 10 centimeters, so I'm going to have pi times 10 squared, which will be pi times 100. And that'll give me the entire thing. But now I need the central angle measure, because that'll tell me what percentage of the area am I looking at. And then when I multiply it by the entire area, I get the final answer. So here I'm going to have 78 times 100, which is going to give me 7,800 over 360 r squared. Oh, sorry, they didn't do that yet. So they just did in our, sorry, I jumped way ahead here. This is where I was getting at. Now, what they're saying is find the portion over the whole. That's your n over 360, 78 degrees, 78. So there's our part over our whole. And then I have it times the entire area. And this is what I was saying here. 10 squared is 100. 78 times 100 is 7,800 over 360. Again, we're going to leave everything in terms of pi so you can be precise. And when we have 78 over 360, it's going to simplify to 65 over 3 pi. So the area of this sector is just 65 thirds times pi centimeters squared. Let's just go over this one more time before we move on. Your area, let's get rid of this part right here. If I just look at area equals pi r squared, that gives me the entire circle. Then if I were to take this and bound just this part, if I take a 78 degree angle here and bound just this part of the circle, I'm going to look at 78 over 360 times the entire area of the circle to get the area of just the piece I'm looking at here. It works the same way on the previous. The part of the circumference I'm looking at times the circumference. If we were to keep moving up in higher dimensions, we would do the same thing, but for the volume of a sphere. That's more in topic 11, and we're really not going to go that far into combining those two ideas, but it will be the same concept. And hopefully we'll be back in class by the time we get to topic 11, and part of your writing assignment is going to be, how could you find a portion of the volume of a sphere? You're going to want to come right back to this video just to remember that it's part over a whole times the formula that gives you the circumference, the area, or the volume of a circle or a sphere. All right. So a segment of a circle is a part of a circle bounded by an arc and the segment joining its endpoints. What is the area of the shaded region? This is your SAT question right here. This is when I have people knock on my door and they say, I really need some help on SAT tutoring. I took geometry freshman or sophomore year and it's completely slipped my mind. This is typically the type of question. Actually, this whole topic is what they come to me knocking on my door for. So let's look at this. We have a radius of 8 centimeters and we have a central angle YRX of 60 degrees, but it doesn't want the whole piece anymore. Last time we had a sector, which goes from it's the entire intercepted part or the bounded part. Now our bounded part excludes the triangle that is made here, and we only want that little piece there. So now it's really the same thing, but we're going to find the area. Well, first we're going to find the area of a sector, which is what we did here. And then we're going to find the area of this triangle and find the difference in those two. So again, was this the same problem? No. So here we're finding the area of the sector, that is this piece and this piece together. And then to find the area of the sector, we get 32 over 3 pi. Then we find the area of the triangle. Oh, one of the nice things about this is, since this is inscribed or drawn inside of a circle, these will always be at minimum isosceles triangles. But let's look at some reasoning here. Since Rx and Ry, that is the two 8 centimeters here, are both radii, and the angle between them is 60 degrees, RYX is equilateral. How did they make that conclusion? Well, if this angle is 60 degrees and these two sides are the same, if opposite angles generate side lengths, for these two to be equal, they have to have the same angle across from them. So if I do 180 minus this 60, the known angle, I'm left with 120 divided by 2. I now have 60, 60, 60. Therefore, this must also make an height, a side length of 8. And we can do the Pythagorean theorem to find the height of the triangle, and we get 4 square root of 3. What they did there is 4 squared plus h squared equals 8 squared. 16 times 3, yeah, it's 48. So we have a height of 4 square root of 3. It's 1/2 8 times 4 square root of 3 gives us the area of a triangle of 16 times the square root of 3. What they did here is they just took 1/2 times 8, which is 4. 4 times 4 is 16. Since that's under the radical, we can't do anything with that. We get an area of this little piece here to be 16 times the square root of 3. So now we're going to take the area of the segment minus the area, the area of the sector minus the area of the triangle to get the area of the segment. Here we are obviously going to have two irrational numbers, so we're going to have to round here, but it's about 5.8 centimeters squared. Here is your overview. This is probably the most important thing you guys can copy down and really just start memorizing it again. The first two just tell you to take part of the circle that you're considering and multiply it by either the circumference or the area, depending on what you're looking for, the highlighted part or not. This is the same thing. Now we just need to do the area of a circle minus the area of the sector to get the segment. All right. So all your homework on 10.1 is due tonight by 11:59 p.m. See my EDSB message about due dates while we're out. Just please make sure you do your homework. We're in quarter 4 now. Absolutely no late work accepted. Absolutely no changing grades. If you don't have it in, you do receive a 0. And I have a script to pull the Pearson assignments at midnight. So 1 minute after it's due, I will have all the information pulled. All right, let's look at some of the homework problems, some things that you're going to see. We might have a little surprise here on number 2, so let's keep our eye out on that one. But let's start with number 1. Given circle with center in, what is the measure of arc ABC? So we're going to go from A to B to C. It wants this minor arc. I'm calling it a minor arc because it definitely isn't more than half of the circle. So this minor arc is 138 because my central angle is 138 degrees. Now, here's something that I may have not really pointed out here. What is the length of the radius on this question? What is the length of R? No, we don't have a defined length, and that is when we can say that these two are equal. If we come to number 2, we can see here that we do have a defined length for the radius of 8. This is where what we were talking about before with the part over the whole and all that is much more relevant to our question. But here, it wants your answer in radians. Now, if you remember, your arc length is equal to theta times r, where here r is 8 and theta is 2/3 pi. So my arc length is 2/3 pi times 8. So this is done rather simply. Let me do it the quick way, and then I'm going to show you it piece by piece, because sometimes people like seeing it both ways. Well, here I know that 2 times 8 is 16, and fortunately we have that answer. So let's look at what I actually did there. So I'm going to look at this step. I'm going to pick it up in blue here. 2/3 pi r times 8. So this is my, I don't need the r there, do I? This is my theta, and this is my radius. So I'm going to make my substitution in there, and I have 2/3 pi times 8. Now the commutative property of multiplication says I can rearrange these in any way I want. And since I have an irrational number here, I'm just going to tack that on the end. So I'm going to rewrite this as 2/3 times 8 times pi. And then when I have 2/3 times 8, what a lot of people forget to consider is this is the same as 2/3 times 8/1 times pi. And that's much easier to see that if I multiply straight across, I get 16 pi over 3 times 1 times 1, which is 3. So then I do have 16/3. If you're wondering why here I have it in the numerator, here I have it standalone, well, this is 16 times pi over 1, or 16/3 times pi over 1. So 16/3 pi is equal to 16 pi thirds. We're going to see it written like that more often than not once we get out of this class. So I want to start letting you familiarize yourself with that. Now let's look at number 3. I'm going to go ahead and erase this stuff just for room's sake. What is the length of arc MPN? So now we've got this. We're starting at M, and we have to go to P and then to N. So that's definitely a major arc, because it is more than half of that circle. It's greater than a semicircle. So let's start this one. Well, I know the entire circumference of the circle. It's going to be 360, and I've already taken out this piece right here, which is 44, and that's going to leave me with 316. So if this was a 1, I can say that MPN is 316, but since I have a radius of 5 here, I have to go ahead and do my part of my whole and all of that. So remember, the formula for that is S is equal to N over 360, and this is length, and length is first dimension, so I'm going to do 2 pi r, which then gives me, let's do a different color. My N is this guy right here. That is the portion of the whole circle that I want. So I'm going to have 316 over 360 times 2 pi 5. I'm going to go ahead and multiply these together and get 10 pi. So now I have 316 over 360 times 10 pi. Well, this is 10 pi over 1, so I can now multiply straight across. I come back here, delete some of this. This becomes 3160 pi over 360. Right? 316 divided by 10 is simply 3,160. Anytime you multiply by 10, just add a 0 to the end. 360 times 1 is that. So now I'm going to start simplifying this. I don't have a calculator on me, so let's just do it the old quick and easy way. And that is If I have a 0 and a 0, I can go ahead and cross those out, and I'm at 316 over 36. 316 and 36 are both divisible by 2, which would give me 158 over 18. Go ahead and move the pi down there. And then 158 and 18 are divisible by 2. It's going to leave me with 79 over 9 pi. 79 is not divisible by 9. It's not divisible by 3 because 7 plus 9 is 16. 4, no. 5, no. 6, no. 7, no. 8, no. So yeah, I'm pretty confident that we can say the simplified version in terms of pi for the major arc MPN is 79/9 pi. Right, this is what your homework's going to look like. I couldn't pull your actual homework assignment up because Pearson's being a little weird tonight. I don't know if it's everyone flooding to get content together for their online class, so I just kind of picked the topic quiz or the lesson quiz and went from there. It will be representative of your homework. Again, let me know if you have any questions on EDSB. You can reply right under this assignment. That way we have a log for everyone else in the class to see what the questions are.